All right, recording is started. Good morning. Where we're at today is we are currently in the middle of section 14.4. This is on tangent planes and linear approximation, and then also differentials, which we'll get into today. The part we ended off with, well, maybe I'll just do a brief recap. So we introduced the idea of a linearization. So the linearization to a multivariable function is a linear function, which does a good job of approximating the function near the point in question. And so we wrote down our linear approximation. We justified this was the case. Our linear approximation is given by the tangent plane at the particular point. And how we can construct the tangent plane is essentially the z coordinate of the point we know on the plane plus the derivative in the x direction times x minus the x coordinate plus the derivative in the y direction times y minus the y coordinate. So this is called the linearization. And the technique of doing a linear approximation is taking our function f of xy, which I've written here, and using the linearization to approximate it. So this is essentially approximation via the tangent plane. So linear approximation is approximation of z equals f of xy by the tangent plane. So that's what it is. So if we can find the equation of the tangent plane, then we just make that into a function, and that's the linear approximation of the, or linearization, which we use as a linear approximation to our function itself. So we did an example of that. And then we introduced this idea of what it means to be differentiable. In contrast to calculus 1, a function in multiple variables is differentiable, not when its derivatives exist, but a little bit more deeper than that. A function is called differentiable if, and I'll paraphrase what this statement in the box says, a function is called differentiable if its linearization, or its tangent plane is a good approximation of the function at that point. So that's what it means to be differentiable. And we could kind of glean this from the statement here. I'll just erase some of my markings. So what we have is a function is differentiable if at a point AB, if we're standing at that point AB and we move a little bit away from it. And if we move a little bit away from it, the value to get back onto the surface again, that's the delta z. That's how much I have to go up or down to get back onto the surface again if I move away in some x direction and some y direction. So the value that it takes to get back on the surface really depends on the derivative in the x direction and how much you moved in the x direction. And the derivative in the y direction times how much you moved in the y direction. And then there's this little extra factor. And that's just because the tangent plane is an approximation to the surface at that point. So this first part in the red box is really just saying how much you have to move by in the x and y direction to get back onto the tangent plane. And then that extra little factor tells us we might need to move an additional little bit depending on how far away we are from the point in question. And that's this delta x and delta y, how far we had to move away from the point we're at. We might have to adjust that by a little bit in height to get back on the surface. But that little adjustment factor, that becomes negligible as we move only a little bit away. So if delta x and delta y are close to 0, that means we haven't moved very far away from the point. And so that little adjustment factor is almost negligible. I don't have to move very much aside from being just on the tangent plane. So this statement here is really just saying that the tangent plane is a good approximation of the surface near that point. And that's what it means to be differentiable. So one of the additional questions you have this week on the homework assignment is to actually look at an example of a function where both the x and the y derivatives exist. So the function has partial derivatives, but it's not differentiable at the point. And you just have to investigate, why is the tangent plane not a good approximation of the function there? And I give you lots of hints to sort of walk your way through why the tangent plane wouldn't be a good approximation, and therefore the function's not differentiable. So that's all.
Can I ask an off-topic question?
Yeah, go for it.
So speaking of the additional questions, have you actually released the crowd mark yet? Because I can't see it. I was checking last time.
So the crowd mark for this next assignment hasn't been released yet, but the questions themselves are available on our course website in the assignments page. So I'm just gonna.
I just want to make sure it's on my account.
Yeah, so no, they're not through CrowdMark yet. So I haven't released the CrowdMark, but the additional questions are posted. I'm just going to. Let me just share my screen for a second here. Assignment 4 is posted as a PDF, and that's available. The CrowdMark portion of it, though, I haven't released the CrowdMark for submission yet. Does that make sense? Does that answer your question?
Yeah, all good. Thanks.
All right, you're welcome. All right, and so there's this warning down below. What this warning says is that this is really a warning about what it means to be differentiable. And I just want to draw your attention to the last bullet point. Having both partial derivatives at a point does not guarantee that a function is differentiable. Or in fact, it doesn't even guarantee that it's continuous. So you could have, you could look at your function and say, oh, I've computed the x derivative. Oh, and I've computed the y derivative. But the function itself may not even be continuous there. So existence of partial derivatives isn't enough to guarantee differentiability. What is enough, however, is this statement in the theorem up above. The theorem above says that if your partial derivatives exist near the point AB, and they are continuous at AB, then that's enough to be differentiable. So the existence of your partial derivatives and the fact that they're continuous, that's enough to guarantee differentiability. So let's have a look at how we could use this criteria. So we're wanting to explain why this function f of xy square root of x plus e to the 4y, why is it differentiable at the point 3, 0? And so the way we can do this is we can just go ahead and compute the x derivative. And so that's going to be 1 over 2 times the square root of x plus e to the 4y times the derivative of the inside function with respect to x. So that would be just the derivative of x with respect to x. So that's a 1. And then what about our f sub y? So our y partial derivative. That again would be 1 over 2 root x plus e to the 4y times the derivative of the inside function with respect to y. So that would be e to the 4y times the derivative of the inside of that, which is 4. And so that becomes a 2e to the 4y all over the square root of x plus e to the 4y. So I cancel the 2 top and bottom.
Are we not missing a part of the derivative for fx of f, like the first derivative?
So we've got the derivative of the outside function, that's a square root. And then we've got the derivative of the inside function, but the inside function is just linear in x. So the derivative of x is just 1. Does that make sense?
So
I can add it in here.
Oh yeah, it makes sense. Okay, I forgot. It's so the first one is derived by with respect to x. Second one's the opposite.
Exactly, with respect to y. So that's the part we are missing, but I left it off because it was 1. Okay, so now we're wanting to use that criteria. So the question is the multivariable function, is it differentiable? And the answer is, well, both f sub x and f sub y are continuous near the point in question. Point in question is 3, 0. And the reason is because what's going on at 3, 0? Well, we've got some denominators there, but those things are not even close to being near 0. So the square root function is a continuous function, x is a continuous function, e to the 4y is a continuous function. So all of that together is a continuous function. It's in the denominator. That's nowhere near 0 because we're plugging in 3, 0, and that's close to 2. So everything is looking really nice here. So because both the fx and fy derivatives are continuous, therefore f is differentiable. Okay, and because it's differentiable, then that means the linearization or the linear approximation is a good approximation of the function there. So we can go ahead and do the second part of the question, is find the linearization. So the linearization, which is L of xy, that's given by the function value at the point in question plus the x derivative at the point in question times x minus the x coordinate of that point, plus the y derivative at the point in question times y minus the y value of the point in question. And so there's our linearization. We can go ahead and work out the individual values. F of 3, 0. So we'll plug 3, 0 into our function f. That becomes the square root of 3 plus 1, or the square root of 4, which is 2. We're going to plug 3, 0 into our derivative. That's 1 over 2 root 4. So that's 1/2 x minus 3. And then the last part is plus the y derivative at 3, 0. And the y derivative at 3, 0, the top is 2 times e to the 0, so just 2. The bottom is a root 4, so we get a 2 over 2, which is a 1. And so that's 1 times y minus 0. I'll just add it in because we got enough room up there. It's just a plus y. So that's our linearization. So there's our linear function that does a good job of approximating our function f at the point 3, 0. And the last part of it says use this to approximate f of 3.1, negative 0.1. So the idea is this function value at that point, which is a point that's close to where we just constructed the tangent plane or the linearization at. So this is approximately given by the value we have on the tangent plane at that point. And that's given by L of 3.1, negative 0.1. And now we can use our tangent plane or our linearization to work out that value. So that's 1/2, 0.1, and then minus 0.1. Oh, did I write 1/2? I think I maybe didn't see anything in the chat, but I think I maybe should have a quarter in front for this one. This value here, that's f sub x of 3, 0. And when we put 3, 0 into our f of x, I get 1 over 2 times the square root of 4. So that actually should be a quarter. So I've got to make an adjustment there. That should be a quarter in front. And this should be a quarter in front down here. There we go. So those are a quarter. So this quarter updates that one to also a quarter. Okay, and so there's our linear approximation for the function value at that point. And we could work this out. This is about 1.925. So it says that if we were to plug 3.1 and negative 0.1 into our function f, we're going to get a value that's pretty close to 1.925. So this is the idea of linear approximation, using the point on the surface that you know stuff about, derivatives and the z value there, and then using that to predict what's going to happen as you move a little bit away from it. As you move a little bit away, you just use the points on the tangent plane as a good approximation to the point on the surface itself. Okay, now one thing I just want to point out here is when I look back at my linearization, what I have is it's given by the point on the surface where you've constructed the tangent plane at. And then when you move a little bit away from that, this is my adjustment factor. This tells me how much I have to add or subtract from my z value of the point in question because I'm moving away from that point. And that adjustment factor is really about, well, what's the rate of change in the x and the y direction? Is the function increasing as you move in the x direction or decreasing? Is the function increasing as you move in the y direction or decreasing? What if you move in a direction that's not entirely in the x direction or the y direction? Then it's a combination in this way of how much you moved in the x direction times its derivative, plus how much you move in the y direction times its derivative. So that adjustment factor is really just telling us how much we have to shift our z value up or down from the point we're starting at, with this f of 3, 0. So that's an important quantity. That's what we're going to be calling the differential. So the differential is precisely that quantity, and I'll just box it here. It's the x derivative times how much you change in the x direction, plus the y derivative times how much you change in the y direction. And so these are just three different ways to represent the same thing. The change in the x and the change in y can be denoted by the delta x or the delta y, or we could just use little dx or little dy for the change in x and y, or we can use this del notation, the script d's for the derivative. So those are all three equivalent expressions, just notation dependent. So that's the differential. And if you think back to calculus 1, the differential in calculus 1 was just the derivative times dy. So here we're just generalizing that. It's the derivative in the x direction times dx plus the derivative in the y direction times dy. And the thing to keep in mind is this tells us how much the z value is going to change if we change our inputs by dx and dy. If I change my input by dx and dy, so I move one of the variables, one of the input values a little bit, the dx value, and I move the other input variable up by a little bit, namely the dy value, then this tells me how my output has to change. And so we can do an example now. So if we're going to find the differential of the function f of xy, which is given by 2 sine x, 3 cos y, the differential dz is given by the x derivative times dx plus the y derivative, or y partial, times dy. The x partial is given by 2 cosine of x dx plus the y partial is negative 3 sine y dy. So that's our differential. And again, our differential is telling us how our output changes if we've changed our inputs by a little bit. Okay, so let's see how we can use this. For the function in question that we've been just working with, let's calculate f of pi by 2 and 0. So f of pi by 2 and 0. So that's going to be 2 sine pi by 2 plus 3 cos of 0. Sine of pi by 2 is 1. Cos of 0 is also 1. So this has a value of 5. Now, the next part of the question is, let's use the differential to approximate the value of f at 29 pi by 60 and pi by 50. So the main idea is 29 pi by 60, comma, pi by 50 is very close to pi by 2 comma 0. So we would expect if the function's nicely behaved, it's nice and smooth, there's no sharp turns or anything like that, if it's a nice smooth function, then we would expect that the value at 2 points that are close to each other, the function value should be pretty close to each other. And we've just worked out the function value at pi by 2, 0. So we should expect that the function value at 29 pi by 60, pi by 50 should be roughly 5 as well. But there may be a slight adjustment factor that we could use to make this an even better approximation, because we could say, well, our x value is not quite at pi by 2, it's a little less than pi by 2. It's like pi by 60 less than pi by 2. So maybe, now I know how much I've moved in the x direction, maybe I just need to figure out what my x derivative is, because then I can multiply the two. That would tell me how my z value is changed by moving a little bit in the x direction. And similarly, I move a little bit in the y direction, namely I'm increasing my y value by pi by 50. If I know what the rate of change is in the y direction, then I can multiply that by pi by 50 and get the rough change in the z value by moving a little bit in the y direction. And so I can increment those additional changes into the picture as well. So I expect that the value to be close to 5, but with some little adjustment factors based on the rates of change. And so what are those adjustment factors? Well, we'll work out our differential. So our differential is above here. We'll bring that down. So this tells us that our differential is going to be 2 times cosine of, oh, actually, yeah, well, why don't we do this? So it's going to be 2 cosine. So what do we have to do? We have to work out the value at the point we know things about, and then use the change in the direction. So this would be 2 times cosine of pi by 2 times the change in the x direction. So the change in the x direction is going to be 29 pi over 60 minus pi by 2. So that's the change in the x direction plus the rate of change in the y direction. That's 3 sine of 0 times how much we moved in the y direction. So that's pi by 50 minus 0. So the idea is we're using our point that we want information about, and the way we're doing it is we're using information at the point we were at. Now it turns out, in this case, that both partial derivatives are 0. We can see that here. Cos of pi by 2 is 0, sine of 0 is 0. So what that means is that our tangent plane at that point in question is actually just flat. So our tangent plane is flat there, which means that if I move a little bit away from it, I'm using just the values on that flat tangent plane to approximate the function. So I'm not getting any changes. So that's where the dz becomes 0 when we calculate it here. It's really just telling us, oh, we've got a flat tangent plane. So if I move a little bit away, I'm not getting an increase or decrease. So the value of the point I'm standing at is a good approximation for the nearby points because it's a flat tangent plane. Yeah, exactly. It's sitting at, we're either sitting at like a local max or a local min. So the other values, since we're using the other values nearby, we're using the tangent plane as the approximation. So they're going to give us just the value of 5 as a good approximation. So the differential, I'll circle that here, our differential is 0. And so the actual question says use the differential, which we've now worked out, to approximate the value of the function at that point. So now we can go ahead and finish that question. The function value at this point is it's closely approximated by the function value at the point we've constructed our tangent plane at, or our linearization at, plus the differential. That's the adjustment factor. And this had a value of 5. This had a value of 0. So 5 is our close approximation. You know, the analogous idea here with calculus 1, I'll draw a little picture. We'll do calc 1 here, just so we can see. The idea is in calc 1, let's say I'm interested in, I got a value here. That's the point I know information about. And I'd like to know if I moved dx away, what's the value of the point up here? Well, if I move, I'll zoom in on this a little bit. If I move dx away, what we would say is, oh, to figure out what my jump is, I just need to know what the derivative is at that point. So I'd work out the derivative at a, I'd multiply it by how much I moved over by. That would give me the jump. And so that's my change in y. So we would then say this value that we're interested in. So if we're sitting here at the value f of a, then the value we're interested in is f of a plus f prime of a dx. Maybe I'll put that in green so it doesn't blend in with the background there. F of a d f prime of a dx. So that is our function value we're at plus how much we moved over times the derivative. But if we're in a situation, so here's the picture we're in right now, we're in a situation where we're staring at a point A and we construct the tangent line there. This is our tangent. And we say, what's the value of the point nearby, say at a point here. If we're using our tangent line, which just happens to be horizontal in this case, then the value that we would use to approximate that red point would be the value on the tangent. And that would just be the value of the point at A, or the value of the function at A itself. So here we wouldn't get any change in the y direction imposed on us by the derivative, because the derivative is 0. And that's what's happening in this picture. I shouldn't say a picture. That's the picture we have in mind for this situation. Is we're at a surface, we've constructed the x and y derivatives, they're both 0. So we've got a horizontal tangent plane passing through that point in question. So all the nearby points, we would use the z value of that tangent plane as an approximation. So that's our value of 5. All right, so just an analog from calculus 1, linear approximations and differentials. We just have an extra variable to deal with now. All right, let's look at an example of how we can use this. And this is probably the most common usage of linear approximations and differentials in applied mathematics or physics or engineering. It's this idea of errors. So for this example here, the dimension of a closed rectangular box, notice I missed the word box there, are measured to be 80 centimeters, 60 centimeters, and 50 centimeters respectively. So we've got this box, we've just measured the side lengths, and we get these values. But because we're measuring, there's some error in our measurements. It could be due to the device we're using to measure. And so that's 0.2 of a centimeter is, we've got an error. Maybe it's just we're using a tape measure, and that's the best we can sort of discern for our measurements is that it's 80 centimeters plus or minus 0.2 of a centimeter. So we've got these errors in our measurements. So if we use those raw numbers, 80, 60, 50, to compute the volume, what's the maximum error in our calculated volume? Because the actual numbers could have been, it could have been, 79.8 and 60.2 and 49.9, for example. Those could have been the actual values. And if we use those to compute the volume, we're going to get a different volume than using 80, 60, 50. So this question is saying, if you use these numbers, 80, 60, 50, with those errors that you know are potential errors in those values you're using, what is going to be the error in your volume? And we can use differentials to do this, because what a differential is, or what a differential, or this idea of linear approximation is to say, let's construct a function and let's use these values, 80, 60, 50, to compute the corresponding value of the function. And after we do that, now let's ask the question, what if our inputs changed a little bit? If our inputs changed a little bit, how is our output of our function changing? And that's precisely what a differential is measuring, how your output changes based on the changes in your inputs. So let's have a look at our rectangular box and our calculations. So we've got our rectangular box here. We're going to compute our volume. Our volume is going to be a function of 3 variables, x, y, and z. Say x, y, z. Maybe I'll label them as x, y, and z. So this is the object we're interested in. This is a function we're interested in, this volume. And we'd like to just go ahead and work out the values. So for x equals 80, for y equals 60, and for z equals 50, we could go ahead and plug those in, 80 times 60 times 50, and get the calculated volume. But there's a problem, and that problem is that we know there's errors in the measurement for x. So x can change by at most 0.2. Y can be changed by at most 0.2, and z can be changed by at most 0.2. So I've written these as dx, dy, dz. Those are the changes. In fact, it's absolute values of those things that we are interested in. The error means that dx can be anywhere between negative 0.2 and positive 0.2. This is an error, also known as plus or minus 0.2. So I'm writing these as absolute values. And so now what do we have? Well, we have that if we use these raw values, 80, 60, 50, with those possible changes to our inputs of dx, dy, dz, what is going to be our change in our output? So we'd like to know, what is dv? What is the biggest dv can be? What is the biggest differential of v? What is the biggest change in v can happen? Well, what is dv? So I'll write the absolute value signs out here. dv is the x derivative times the change in the x direction, plus the y derivative times the change in the y direction. And this is a function of 3 variables. So we can just continue on. There's no change really that happens from 2 variables onward. The pattern still holds. So then it would just be the change in the z derivative times the change in the z direction. And that's what that statement up above says. More than 3 variables. There's the formulas, but they're just the same as they were with 2 variables. You just add an extra term on the end. And same what happens with 4 variables, 5 variables, 6 variables. You just add an extra term for each variable on the end with its corresponding derivative. Okay, so we've got our differential now. What is v sub x? So that's our derivative of v with respect to x. That's y times z. That's times dx. Our derivative of v with respect to y is x times z dy. And our derivative of z with respect to, sorry, our derivative of v with respect to z is x, y, dz. So there's our expression for our differential. And now we're interested in the particular case. So instead of rewriting these things all over again, at these particular data values, we get that this is at most 60 times 50 times, well, I'm going to do one more step here. Actually, before I write this in, the additional step is, you notice that my dx, dy's, and dz's, I'm going to want to plug values in for those now. But the problem is I don't have exact values. I have upper bounds on their magnitude. So the next line I'm going to write in is just that this absolute value is less than or equal to. And since y and z are all positive, it'll be y times z times the absolute value of dx plus x times z times the absolute value of dy plus x times y times the absolute value of dz. So I've just pushed the absolute values in, said, I'm looking at the absolute value of a sum. Well, that would be less than or equal to the sum of the absolute values. And now that means I can go ahead and plug these values in. 60 times 50 times 0.2 plus 80 times 50 times 0.2 plus 80 times 50 times 0.2. So that's going to be 0.2 times, what do we have? 60 times 50, so 6 times 5 is 30, times 10 times 10 is 303,000. So we've got 3,000 plus 80 times 50, that's 4,000. Oops, I might have used the same value in the wrong spot. Sorry, the same value it looks like I've used in two different spots. I better check this. Z was 50xy. That's where I made a mistake right there. That should be a 60. That should be a 60. So I just read the information above wrong. And so that would be then 4,800. And then we're multiplying by 2/10. So we can work this all out and we get a value of 2,360 cubic centimeters. So that's how much our volume could be off by calculating with just those values of 80, 60, 50. Even though we're off by just 2/10 of a centimeter in each measurement, each of those three measurements, our total volume could be off by over 2,000 cubic centimeters. So the question is, should we use the equal sign? It may look like I'm using it, but I'm not, because I've got a chain going on down here. So the absolute value of dV, so the maximum value in some sense I'm working out is how big is this differential. It's equal to these first two expressions, but then it's less than or equal to everything that follows below. So when I read this off at the end, we've got that dV is less than or equal to 2,360 cubic centimeters. And so that is our error in the calculated volume. We could be off by as much as 2,300 cubic centimeters. Yeah, so this is how differentials are commonly used in practice. They come up in error calculations. So whenever there's an error involved in a measurement, whenever there's an error involved in the known values of a particular problem, the linear approximation or the differentials come into play, which tells you how those errors in inputs translate to errors in outputs. All right. So that's it for our section on linear approximations and differentials. Yep. So I'll just back up. The question was, so we've got our function v. I need to know what v sub x was. And I then took the derivative of xy times z with respect to x. So that gave me a yz. And similarly for the other ones here, we needed to know what v sub y was. And so that was our derivative of xyz with respect to y, which was just xz. And lastly, the derivative with respect to z was that quantity there, x times y. Yeah, thanks for that question. All right. So now what we're going to do is we're going to back up just a little bit. So I'll sort of paint the picture of what we've done. We introduced in chapter 13 vector valued functions. We figured out what they look like. They were curves in space. And then we took their derivatives, and those were the tangent vectors. And then we sort of said, okay, that's one kind of object that we've got, these space curves. Now let's go ahead into chapter 14 and look at surfaces. So we introduced the functions of multiple variables. We looked at graphing them. Then we looked at tangent planes and linear approximations and the relationship to partial derivatives. And so in both cases, we introduced an object and then its derivatives. And then we introduced a surface and then its derivatives. Now what I want to do is I want to go back to chapter 13 and do a little bit more with the derivatives. And then after we do that, we'll come back to chapter 14 and we'll do a little bit more with the derivatives. So you can think of it right now, we've just introduced two kinds of objects and the geometric interpretations of what their derivatives mean. And now we're going to see what else can we do with the derivatives? What further questions can we investigate? And for this one, sorry, it's not 13.4, it's 13.3. So now we're going to come back to space curves, and we're going to look at questions involving arc length and curvature. And we're going to see how these are related to the derivative. So just a quick reminder from Calculus 1, if we had a plane curve, so parameterized curve from Calculus 1, x is f of t, y is g of t, then we can find the arc length by integrating the square root of the sum of the squares of the individual derivatives. And we're going to see why this was the case. So we actually proved it and it was related to the Pythagorean theorem, etc. But we're going to see a more natural interpretation of why this should be the arc length of a curve and how it generalizes to space curves, so curves in 3 dimensions. So why is this? Well, I'll draw a little picture. Maybe I'll fit the picture in between these two. Yeah, I'll fit the picture in here. So the idea is we've got our space curve. In this case, I'm just drawing it in the plane. And along our curve, we've got, for a given point, we've got a tangent vector that's given by r prime of t, if this curve is given by r of t. And the idea with this tangent vector is that we can compute it. It's f prime of t, g prime of t. The length of it is given by the square root of f prime of t squared. Now we're just using the length of a vector here. It's just the sum of the squares of its components, g prime of t squared. And if we think about it this way, so imagine this is a particle moving around in space. This is the path it's taking. What is r prime of t? Well, do we have a physical interpretation of what r prime of t would be? I've got this particle moving along this curve. Right at that moment when it passes through that orange point, what is r prime of t actually representing as a physical quantity for that particle that's moving around? Do we have some intuition as to what this would mean? It's the tangent to the curve. Yeah, so it's the direction that if we're imagining this particle being like on a roller coaster track, and all of a sudden the seatbelt let loose, or the thing holding the cart to the track lets loose, this is the direction that that cart would go flying off into. It's, yeah, and in some sense, exactly, Eduardo, it's like, it's the velocity vector of the escape. So if you escape off of this track, that r prime of t is your velocity vector. So if r prime of t is your velocity vector, as a velocity vector, there's two quantities that it has. There's a direction, that's the direction you're flying in, and the magnitude. What do you think the magnitude is as a quantity? So there's direction, velocity consists of two things, a direction and exactly a speed. So the magnitude is the speed. So this, I'm just drawing on your intuition. This is all of the next section, 13.4 is all about these concepts, but I'm just trying to draw on your intuition here for a little bit. This is speed. And so if that's our speed, then integrating speed is our distance. So if the derivative of our position, our derivative of the distance traveled, or the rate of change in our distance traveled is speed, then the integral of speed would be our distance traveled. And that's what this formula is really saying. Saying integrate the speed function and you get your distance traveled. So that's just coming from sort of the natural physical context. So that is just taking the formula that we had in Calculus 1 and just looking at it through slightly new eyes. This is now not so much about integrating the square root of the sum of the squares of the derivative components. It's really just saying you're integrating the speed function. And so that's what I've written down here in the definition box, is that this also holds true for higher dimensions as well. So for space curves, if we've got a space curve, r of t, given by f, g, and h are our component functions, then the arc length, the distance traveled by the particle along that curve, is given by the integral from a to b, so where you start to where you end. And we could write this in terms of the magnitude of the derivative vector. And this, again, would be interpreted as speed. So we get that distance is the integral of speed. Let's go ahead and use this to calculate some arc lengths. So let's find the arc length of the circular helix with this vector equation. And we're just going to use that result that's written, the one I boxed above, the blue box. We are just going to integrate the speed function. So in order to get the speed function, we need to work out the derivative of the vector function first. So that's the derivative of cosine of t, that's negative sine t. The derivative of sine of t, that's cos of t. And the derivative of t, which is 1. So now we can go ahead and compute the length of this, in other words, the speed. And that's going to be sine squared t plus cos squared t plus 1 square rooted. Sine squared plus cos squared is 1. So I get that's 1 plus 1, or in other words, this is square root of 2. So there is our speed. What we get as sort of an extra aside to this is that for this particular particle that's traveling along the helix, sort of spiraling around, is we've just worked out that even though the tangent vector at any given point is sort of changing directions, this subsequent calculation says that the magnitude of that tangent vector is always the same. It's constant. It's the square root of 2. So the tangent vector always has the same length. It just points in different directions as you move along the curve. So this is what we call a constant speed curve. The particles traveling around it with a constant speed. And that's what we need in order to work out the distance traveled, or the arc length along the curve. So the arc length along the curve is given by the integral from 0 to 2 pi, since that's what we're interested in. We want to know from the point 100 to the point 102 pi. I can just look at that last coordinate there. That's the t value. And so this is saying that we're going from t equals 0 to t equals 2 pi. So those are my limits of integration. And I'm integrating the speed function. So that's 0 to 2 pi of root 2 dt, or in other words, it's 2 root 2 pi. And so that's how long one spiral of the helix is. So if we're looking at our helix, when t is equal to 0, we are starting at the point 1, 0, 0, and then we're going around to 2 pi. So our particle is sort of traveling around. Try to get these on top of one another, something like that. So there's our helix, our going around one revolution, it's around the backside, and then it comes out front again. And what this says is that for one sort of revolution up the helix, this has a length of 2 root 2 pi. That's how far the particle has traveled. All right, so we'll stop it here today. I'm glad I got to this point because this is the first step in this section, is to just talk about how to get the length of a curve between 2 points. The next part of this section is to turn this into a function and to change that upper limit of integration. I'll circle it here, this 2 pi. If we made that into a variable t, let's say, and so now we're constructing a function that just measures the length from the starting point 1, 0, 0 all the way out to whatever point we want corresponding to the parameter t. That creates a function that's known as the arc length function, and that's what we're going to dive into next day. But for right now, we just worked out the distance between 2 points on a particular space curve. So we'll stop there.